now we're going to introduce the concept of potential energy and potential energy functions, and as it says here, they are definitely one and the same. So when they talk about the potential energy, they're really talking about potential energy functions that allow us to calculate numerical values. Now, for this page of notes, I'm going to introduce the potential energy functions for springs and gravity without proof. So we'll talk in more detail about the potential energy for springs and show more details to mathematically where they come from in a couple pages of notes. But for right now, we're just going to introduce them because most importantly, we want to talk about potential energy as a concept. So let's see where we're going. Kinetic energy we already know about. Kinetic energy is the energy of motion, and that's, of course, Ke, K, 1/2 mv squared, where the v is, of course, speed. Always positive, right? 1/2 mv squared is always positive. The smallest kinetic energy value you can have is 0 when you have no speed. Now, potential energy conceptually is going to be that amount of energy that can potentially be converted into kinetic energy, and our designation we'll talk about informally as PE, potential energy, and then formally the math variable U. Now, as we're going to see, a couple points to note about potential energy and potential energy functions. Potential energy can only be specified for conservative, that is, those path-independent forces for us, only springs and gravity in this course. Friction has no ability to convert the work done by friction into kinetic energy. So we cannot define a potential energy function for friction, for example. There are definitely, as it says here in number 2, specific functions, mathematical equations that describe the number of joules of energy that can be converted into kinetic energy. And please get this into your notes. I said I'm giving it to you without proof on this second page of notes, but we will talk about it more formally in a couple of pages. So the potential energy for a spring, 1/2 kx squared. The potential energy for gravity, mgy. Notice that the potential energy for a spring will always be positive because of the x squared. Potential energy for gravity will depend on the positive or negative that we're going to use when we plug in the y, and we will always use positive 9.8 for the g. So please make sure you get all of these annotations into your notes. Now, the most important thing conceptually I want to talk with you about on this page of notes is that potential energy is always the energy associated with the change in position, okay? Individual potential energy values, as we are going to see, have no physical meaning. We have to talk about the change in potential energy. Well, let's just take gravity here as our simple example. So we're going to consider a 1 kilogram mass. It's our 1 kilogram mass falling 10 meters. So we're going to calculate the potential energy value. We're going to use this equation, right, to get a joule value at 10 meters. So mg positive 10, positive 9.8 joules. The object is going to fall 10 meters down to position 0, ground, and it has a joule value, a potential energy joule value, again using this equation, mgy, m1, g 9.8, y is 0, so 0 joules. And if we look at the change in potential energy, final minus initial, there was a negative 98 joule change in the potential energy, and that negative is going to correspond to loss. So we lost 98 joules of potential energy. Where did it go? Well, we'll see more formally in a couple pages of notes, and hopefully it's not surprising. It went into kinetic energy. In terms of individual potential energy values not having specific meaning, those joule values, let's say instead of going from position 10 to position 0, we went from position negative 10 to negative 20. Now, we still went down by 10. Now, you're going to see some things stay the same, but some things are drastically different. So if we calculate the potential energy value, again, mgy mg y. The negative goes in for the y. Now we don't have positive 98 joules. We actually have negative 98 joules. Huge difference in those values. Our potential energy at negative 20 then is mg y negative 20, negative 196 joules. But notice the change in potential energy. The delta y, as we went down, remains the same. That's negative 98 joules. So while the individual joule values have no physical meaning, meaning that if you told me I have 0 joules of potential energy, what does that mean? Well, I can't tell you what it means. It just means you're telling me you have 0 joules of potential energy. What I need to know is there going to be a change in potential energy by going up? And if the delta U goes up by 10, then you gained 98 joules. If you told me the same thing, that you have negative 196 joules down here, what does it mean? I would have to say, I don't know what that means. You have to tell me how you're going to change your position. And if you told me you went up 10 meters, then I would say your delta U was, again, positive 98 joules. Negative 196 plus 98, negative 98. So individual, again, as always, please make sure you annotate completely. Individual potential energy values have no physical meaning, but the change in potential energy absolutely has physical meaning. So for the next 2 pages of our notes, you'll be doing some example problems, and then you'll be able to watch the solutions in the following video.